All right, so in this part, we're going to talk about how are we going to compute these metrics for computing a final answer. So we discussed that we're going to compute P first, which is probability that number of heads A gets is equal to the number of heads which B gets are equal in the first segment where both of them have n coins. Okay, and then we're going to also compute X, which is probability that A gets less heads than B in the first segment, but just by one head. Okay, so let's get started and compute P first. Okay, so here again, what's happening is A and B both have n coins as designed, right, in our first segment, and we're saying that they toss, they toss these coins, and they are supposed to get equal number of heads. So what are the possible situations? So what is the number of heads that both of them can get? Okay, so let's say the number of heads, it could be that both of them got 0, it could be both of them got 1, or both of them got 2 or 3, so on all the way till n. Okay, and let us say if they just got, say, k heads, a general number, what is the probability that both of them get k heads after tossing n coins? Let's compute this probability. So let's say pk. Okay, it's basically A and B getting k heads in segment 1. Okay, let me denote it as pk. So this is actually equal to nck times so what are we doing? We're saying out of n tosses, or out of n coins, n coin toss, choose any k coins, and they should come up as head. So therefore half to power k, and the remaining ones, because it's a fair coin, the remaining ones have to come tail. So 1 by 2, because it's the probability of the tail, to power n by k. Okay, so but this is just for player A. We also need something for player B, and it's going to be the same thing. And coins, pick any k should come up as head, and the remaining ones should come up as tails. This is for B. So if I have to simplify this further, this becomes equal to nck half to power k plus n minus k, nck half to power k plus n minus k. Okay, so this will simplify to nck half to power n times nck half to power n. And I can simplify this further as half to power 2n nck times nck. Okay, so but this was just for only k heads, and we want to compute this for all possible heads which A and B can get in the first segment. So the final answer is going to be this: the probability of heads, number of heads which A gets equal to number of heads with B in the first segment is going to be summation from k to n over 2 to the power 2n times nck times nck. Okay, and this can be simplified further as 1 by 2 to the power 2n. I'm just rearranging stuff here. Summation from 0 to n nck times nck. Okay, now this looks like a weird formula. What are we going to do about this? This is now nowhere closer to a number or probability that we can work with. So here we leverage something called as hypergeometric distribution normalization, and I'm going to take you quickly to this world of what I'm talking about to simplify and compute this answer further. So what is a hypergeometric distribution? So let's say you have a population of n size, capital N here. Just a second, let me get my pointer. Yes. So you have a population of capital N size, and out of this population you have k successful samples. Okay, k successful samples. What we want to do is we want to find out the probability that if we take n draws, if we take n items from this population, we get k successful items. Okay, k successful items. So how we compute this? So this is something given by a hypergeometric distribution, and it's fairly simple if you understand fundamental concepts about combinations. And the answer is, let's say probability P of getting k success out of n draws is equal to, so what do? Let's first select k successful items, but we need to find them out of the successful samples in the population. So we choose from capital K, small k items, and then because in our draw we just want k items which have to be successful, no more, no less. So therefore the remaining ones have to be from the non-successful items in the population. So therefore it becomes n minus k times n minus k c n minus k. Again, n minus k is all the non-successful samples in the population, and in our draws we want n minus k non-successful draws. So therefore we choose n minus k. Now these are all the possible ways in which you can choose, in which you basically can compute n draws with k successful successes in this setup. Okay, but this is not a probability. This is all possible ways. To compute a probability, we need to divide by all possible ways in which you can divide it, in which you can take n draws out of this population of capital N size. So we divide it by n cn, capital N in the superscript. Okay, now this is for k successes out of n draws, and you may be thinking, why am I telling you a distribution here? Well, here comes the interesting part. So think about this. Let's say you had n draws. Okay, what are the possible successes you can get in the setup? You have n population size, you have k successful samples, you draw n items, and you have k successful draws in these items. What are the possible successful number of successes you can get in n draws? It can be either 0, it can be either 1 or 2, 3, all the way till n. Either one of them. Okay, either you won't get any successful item, you get just 1, or you get 2, or you get all successful items. One of them, again, they're mutually exclusive events. Mutually exclusive, right? Because let's say if you took a draw and you got 4 successful items, that's all you got. You can't have 3 or 2 at the same time. And they're also exhaustive items, right? They're also exhaustive events, not items. And the reason is, again, if you have n draws, you can't have more than n. You can't have less than 0 successful draws, okay? Therefore, probability of 0 success out of n items, out of n draws, or 1 success out of n draws, or 2 success out of n draws, similarly, all the way till n success out of n draws is going to be what? So think about it. It's mutually exclusive and exhaustive setup. So therefore, it's going to be just sum of these probabilities. So 0 success, I'm just quickly denoting it like 0 out of n, plus 1 out of n, plus 2. Similarly, we add it up till we get n success out of n draws. Okay? So, and what should they sum up to? They should sum up to 1. The reason is because you've considered all possible combinations here. All possibilities have been captured. Okay? Like we mentioned, n draws, any number of successful items have been captured here. So therefore, the sum of these probabilities should be equal to 1. So what we can summarize this as, we can say the sum of k items, let's say k being the number of success from 0 to n, probability of k success out of n draws is 1. Okay? And now if you start applying the formula of probability, which we computed here, like this one, right here. If we use this one, we can quickly find a property, which is sigma k is equal to 0 to n, kck, n minus k, cn minus k, over ncn, okay, is equal to 1. If you simply substitute the probability formula from a hypergeometric distribution, which you can find it right here. Okay? This was for k successes out of n draws, and now we're just capturing all the possible successes that we can have out of n draws. Now, if you notice that this thing is actually variable independent, you don't have a variable here. right? So, I mean, what I mean to say variable is k. So variable is the number, the variable which we're using to iterate here is k, and it's present here, but it's not present here, right? So I can quickly take this and put it here. And what I have is, I have this formula which is sigma from k equal to 0 to n, k, ck, small k, n minus k, cn is equal to ncn. And just for clarity, I'm just going to quickly take this and move it here. So what we have is this very interesting property. We see that they're product of two binomial coefficients, and if they can be written, if they can be written like this, then we can quickly equate them to, something which is on the right-hand side of this equation. Okay. Now remember this. We're going to go back to our question and see how we can use this. Okay. Now let's come back to our question, and let's quickly also use the property that we just saw. And this property was, I'm just going to quickly write it right here, was sigma k is equal to 0 to n minus k, k small k is equal to n cn. Okay. Now let's see if I can write this formula right here, this part right here, in the form of this guy. If I can do this, then I can convert this product of binomials, a summation over product of binomials, into something very similar here. Okay, and I'm going to use a property which I call as, it's a binomial coefficient property, which is NCR is equal to n minus r. Okay, and if you don't know this property, I highly encourage you to look it up. It's very simple. It can be easily computed using the formula of NCR, which is n factorial over n minus r factorial times r factorial. Just rearranging stuff, and you can easily get this property. Okay, so now let's quickly go back to the problem we were trying to compute, which is the probability that A and B get equal number of heads in the first segment, and that is equal to 1 over 2 times bar 2n, sigma k is equal to 0 to n. And now I'm going to use this binomial property, which is n minus k, c and k. Why am I doing this? Because I want to write it in a form which is as close as possible to this person here. Okay. Now, if you do a quick comparison, I'm just trying to bring it in a form which is as close as possible. And this may take a little bit of a trial and error, but if you look very closely here, what I'm going to do is I'm going to convert this in an identical form as this formula here. So here what you see is, by comparing, you quickly see n is equal to 2n, okay? And k, and if you have say k dash, n dash, let me just make differential, to differentiate it further. What you see is k dash is equal to k, and n dash is equal to n here, because it's literally identically written. Capital K is equal to n as well, okay? Now, using this formula here, what we can easily find out is, using this property of hypergeometric distribution normalization, we get this becomes equal to c to ncn. All right, this, which was the probability of A and B getting equal number of heads in the first segment, this was indicated as P. This becomes equal to 1 over 2 to the power 2n to ncn. Okay, so we have the first part. First computation is done. Hooray! And let's talk about the second part, which is computing X, the number of probabilities of head A getting less heads than B in the first segment by 1 head. Okay. All right. So now we're computing X, which is the probability of number of heads of A being less than the number of heads of B in the first segment by 1 head. Okay. So, okay, let's think about this. A and B both have n coins again. Okay, and let's see if they toss all their n coins, what is the possibility in which, A and B can get heads in a way that A has less one head than B. Okay, so let's say number of heads A, B. So it can be the case A gets 0 heads and B gets 1 head, A gets 1 head, B gets 2 head, A gets 2 head, and then B gets 3 head, and so on. And finally, you would have a n minus 1 heads and b gets n heads. That's the maximum possible situation. So if I have to talk about a general case k, then I can say, let's say k gets b gets k heads, and a gets k minus 1 heads. Okay? So now let's compute this probability of the situation. So probability a gets k heads, a gets k minus 1 heads, and b gets k heads is, let's do it for first for person k. So you have n coins, you draw k minus 1. We want k minus 1 heads, so half times power k minus 1, and then remaining we want them to be tails. Okay, then for second person, nck, k heads, which is b, and n minus k tails. If you simplify this formula further, you get nck minus 1 times nck times half to power n times half to power n. Okay, and this becomes equal to half to power 2n nck times nck minus 1. So this is probability that a gets k minus 1 heads and b gets k heads in the first segment. Okay, and now this is just one case. We want the answer for all these possible cases which we have outlined here. Okay, so how do we do this? Why are we doing this again? Because these are all the possible situations which are acceptable for our criteria, right? So the probability of heads a less than b by 1 in first segment is equal to summation over k is equal to 1 to n, where a gets k minus 1 heads and b gets k heads. A gets k minus 1 heads and b gets k heads. Okay, so this is going to be equal to what? We just computed it right here. We're going to use this. So this becomes sigma 1 to n half to power 2n nck minus 1 times nck. Okay, now again, using the property of the binomial coefficients, I'm going to rewrite this thing as 2n minus n, just writing n in the superscript as 2n minus n, and the denominator I can write it as n minus k minus 1, okay, times nck. This again, if I have to simplify it further, I can quickly do it like this. So this is simplified form. If you want to start comparing it to the earlier property we had, I'm just going to quickly write it again. What was the earlier property? The earlier property was k from 0 to n minus k, okay, n dash minus k dash, capital K to k dash is equal to n c n dash. Okay, this was the property we computed from hypergeometric distribution normalization, is the name that we give it to that formula. And let's try to see if we can make a comparison here. So if we make a comparison, what we see is we saw k is equal to n, and k dash is equal to k by comparing this and this. And here we compared this with this. Then k dash is equal to k. Then we also saw that n is equal to 2n, and we also see n dash is n plus 1. Okay. Now there could be a corner case where k is equal to 0 is not being considered, but again, it's not defined for a negative binomial coefficient. That's why we've ignored k is equal to 0 here. Going further here, so this becomes equal to 1 by 2 to the power 2n, and this becomes equal to nc n dash, and nc n dash is 2n n plus 1. So we have computed this thing here as well, which was indicated by x. So x is equal to this. Okay. Well. This is a lot of heavy lift, and now let's just add up all let's just bring everything together. And if you remember, the formula, or basically the answer we were looking for, is right here. Okay, so this is y plus 3p by 4 plus x by 4. Okay, and we had decided we're going to compute p and we're going to replace y. So y is going to be equal to 1 minus p over 2. Okay, and we're going to use this formula in here. And I'm just going to quickly go to the last page to show what we're going to compute now. Finally, the probability of A getting more heads than B in the overall picture was y plus 3 by 4p plus x by 4. Okay, and we also knew that y is equal to 1 by p by 2 using equation 1, which we were just remarking a few minutes before. So this becomes equal to 1 over 2, 1 minus p plus 3 by 4p plus x by 4. And now we have the answer to x, we have the answer to p. So I'm going to quickly rewrite this as half times 1 minus, what is p? P is, this is the p we're looking for. So it gets 1 by 2 to the power 2n, 2n cn. 1 by 2 to the power 2n, 2n cn, plus 3 by 4, plus 3 by 4, times half to the power 2n, 2n cn, plus x by 4, which is 1 over 4, times 1 over 2 to the power 2n, 2n cn plus 1. This computes a final answer right here. And if you manage to get this through without looking at solution, I would say you're a superstar, all right? And if not, that's perfectly fine. These problems are supposed to be practiced and not supposed to be known before by any normal sane person. But I hope you generally appreciated the complexity of the problem and were able to crack through it with me. If you found it hard to do it by yourself, that's completely fine and it's understandable and normal as well. What's important is you try to understand and go step by step as you go through this problem. If you can crack a part of it, as we discuss, then you should have just pause the video and try to go through it. But if you couldn't, that's fine as well. Just work through this problem and give it a few hours, maybe overnight sleep, and tomorrow or whenever next time you want to come back, just look at the problem and try to solve it yourself. If you really understood it well, you'd be able to do it. Otherwise, see if you're stuck somewhere, maybe go to that segment of the video, try to understand what was the solution, and then try to proceed to work it out yourself. The ideal situation you want to have is when you're able to go through the problem from end to end yourself without having to look at the video, and that's where you would say, you were in good shape to do this problem. Again, this is a hard problem, and the reason I'm bringing it out is because if you're able to solve these kind of problems, a lot of interview problems will become much easier for you, and you'd be much more confident when setting in the interviews. Okay, so with this, I would like to again thank you very much for staying with me in this video and working through this problem. I know it could be uncomfortable, but there's also this joy of really having to solve a problem like this through the end. And I'm hopeful that you are able to shortly after watching this video, after a few times, you're able to solve this problem from end to end by yourself. So good luck with your interviews again, and next time we'll be coming up with the next problem of ours, and it's going to be another probability-based question. So till then, goodbye and good luck.